about things that goes in a circle. When you're going slowly, notice the weight is in the middle. But as the speed increases, start to push to the outside. And the faster I go, the higher it goes. It goes faster. And it goes higher. I'm afraid it's actually going to come loose and go flying. If I let it go flying, it's going to fly. It depends where we are. It's called tangential acceleration. So when things are spinning, the velocity is changing. The velocity at this point is in that direction. The velocity at this point is in this direction. The velocity at that point in that direction. The velocity will be in that direction. The velocity will be in this direction. So if my string actually breaks right here, the whole thing will go flying in that direction. If it breaks here, it's going to go flying in that direction. If it breaks here, it's going to go flying in this direction. Well, why does it go to the outside? What makes it go to the outside? Well, there's a force here, is pushing. We're going to talk about something called centripetal force. In the book, actually, our book uses calculus. We found that there's an acceleration at these points. That acceleration equals v squared over r. And it changes direction. R is my radius, that distance. And v is the velocity, how fast that thing is spinning, linear velocity. Well, we know F equals ma, that's Newton's second law. Since my acceleration is v squared over r, then the force is called what? M times v squared over r, or m v squared over r. And our book labels that FCP. Anyone knows what that means? Why they're called CP? Centripetal force. Centripetal. The name actually center seeking, that's where it came from, toward the center there. So that's why when you go on a ride at Six Flags or any of these amusement parks that looks like a swing, everyone starts to push to the outside. The faster they go, the higher you are lifting. It's almost horizontal with that thing. I forgot there's a name for that ride. Anyone knows? Looks like a swing.
The skyscraper?
There's a lot of people sitting on
the skyscraper, the tall one, that like
yeah, spins around, but everyone like in a it looks like sitting in on a swing there in a basket.
The swings,
yeah.
They have multiple ones of them, but there is the biggest one. That is the skyscraper. No, the skyscraper, I believe it's called. It's been there since like 2014.
But that's actually what happens too. You have a force pushing the roller coaster. And people say, well, how come people when you go on the roller coaster, how come people don't fall out of it when it goes in a loop? Because you'll see that ride goes like this. It comes like this. And down here, you're upside down. There's your head. How come you don't fall down? Oh, this one, his head's right there. Our head. Yep, there we go. That's the guy who just lost his hat. You're on that ride. You're going upside down. How come you don't fall? If I take my coffee and flip this cup upside down, what will happen to that coffee?
Spill.
Oh, yep. But if I spin it fast, I bet you it's not going to spill. Mm-hmm. I'm not going to try it. Yep. I don't want to wear my shirt. Get a bright color shirt, they'll spot it there. So the reason actually that you don't fall down, when you look at it when you're at the top there, it is designed, there's two forces acting on you. You get the weight down, which is mass times gravity. And you actually have a force pushing upward, that's your centripetal force, which is mv squared over r. For you not to fall down, to slide out of this, that means what? That force has to be bigger than this force. If that force is bigger than this, you're not going to fall down. If this force is bigger, you probably won't even make it to the top. You get to this point, then you roll backward. So you want mv squared to at least equal mg. At least. When you're right there, you're in zero gravity. If you're at the top, you're zero gravity at that speed. Equals the weight. Centripetal force, that's this one, FCP, mv squared over r has to equal to mg. Well, the mass is the same. That says, doesn't really matter how heavy you are, what your mass is. Your velocity square, when they design these, you want to make sure your velocity square is what? Equal to r times g, the radius. Or velocity is going to be the square root of r times g. So if you design these right such that the velocity of the top is this number or bigger, you will never fall from that ride. So, for example, if 10 miles per hour will make it equal to, make it 11 miles per hour. You know, then you stay there on the top.
That one actually looks like Mind Eraser.
This one?
You just, yeah, the Mind Eraser, you have a Batman ride too.
Yep.
Like it goes in a big loop.
Big loop?
Yeah.
Does it keep spinning?
Nope.
Just one time?
Go one time.
Okay, because if there's more than, when you get to the bottom, once you start going at that speed, you know, what happens when you're on the bottom? How much force on you?
Twice as much.
Twice. Why? Because you get this one pushing down. If you're on the bottom now, you get the weight down, and you get what? mv squared over r pushing down too. If it was like this, if you're on the bottom of that ride now, you get your weight down, and you get this force pushing down, so you feel like 2G on you stuck there. Most of the rides at Six Flags and all these places design on that principle. The one where the floor drops and you're stuck to the wall, yeah, the rotor is designed on that principle. Because they make sure that the force pushing you against the wall is mv squared over r. You get your weight down, you get the friction force pushing upward, try to make sure all these values so you don't slide. And if you notice that ride, what is the wall made out of?
Carpet.
Carpet. Why carpet?
Friction.
Good friction. First, it's soft on your back, so you're not gonna make it hard. But also the reason it's carpet, they could use leather there and foam behind it, but carpet is a good friction, so you're not gonna slide down. You're gonna stay up there. Your car on the road, actually, same thing. When your car makes a turn on the road, you're entering a tight turn, and you'll notice the speed limit will be posted. They go, okay, you're entering this way. That's your car there. It's a speed limit, 50 miles per hour, 60 miles per hour. The reason, they know what the radius of that road is. Now, you're entering the turn here at a speed. There's a force pushing you in that direction. And that's mv squared over r. Now, hopefully you don't go flying in that direction. And the reason you don't go flying in that direction is why? Friction between the tires and your car. Your car is now moving in this direction. It's going forward. Your car is traveling this way. That's the direction you're moving. But in this direction, you're not moving. So you have static friction, actually. So here you have static friction, which is mu s times n. You can, wait a minute, I thought static friction is for something that's not moving. You are not moving in this direction. That's why I'm US. So the reason actually you don't go to that side or come down this way, these two guys must equal to each other. That's what happens. And we can figure out what the maximum speed should be. What's the normal? Again, imagine this is my car on the road. Now the car has a weight down on the road, right? Which is mg. What's the normal force equal to? mg. The m's will cancel each other out, so that's why I said, how do they know what the speed is? They don't even know how heavy my car is. R times mu s times g equals velocity squared. What's the velocity equal? R times mu s times g, and take the square root of that. So that's why they can tell you the speed, maximum speed here or speed limit should be that number when you're making that turn. Now, if I was doing this, and let's say we're only going to use this road when it's dry. We looked at US for rubber on concrete. What was the number? Between 1 and 4. When it's wet, is 0.7. Just to make sure, because you know when you say speed limit is 70, we go 80 miles per hour. So if US is 0.7 on a wet road, I might, for my calculation, use a 0.5 to give me some room.
Does that say mu-s or
mu? Mu-s. Oh, yeah. Yeah, it was a 2, yeah. Mu-s. Yeah. So I might use mu-s 0.5, and I'll measure the radius of that circle there, and I know what gravity is, and we can post that speed. Maximum speed at this turn or reduced speed to 40 miles per hour. And again, I use 0.2 or 0.5 because I know in this direction, tires on a dry day between 1 and 4. I'm using a half because people like me, I'm one of them, I always try to go a little bit faster to see how fast I can turn before I feel the car slipping under me.
So how do you get the radius if it's just...
Well, they measure it. Yeah. Just go up from here to this, because that's part of a circle. They just go up with the tape and go, let's measure that distance. Well, that doesn't work for car racing. Because if you look at the speed, like let's take a radius, I don't know. What's a good side radius you're going to turn? Is 100 yards, 100 meter? That's 200 meters. That's 2 foot length of a football field, that circle. It's a big circle. But even a R equals 100 meters. That's a huge circle. Watch what the velocity is. 100 times mu-s. And mu-s is what? 0.5. I'm using 0.5 here because I'm really trying to make it small. Times gravity, which is 9.8. I'm going to take the square root of that. $490, take the square root of that. It's 22.1 meters per second, which is in miles per hour. About 50 miles per hour. This is reduced speed to 50 miles per hour. Knowing you probably can go 100, you're still going to be okay. Because we have to make sure we put some room for safety here. Or if it's snowing and your tires are bad, that number probably 0.7. So we still have some room here just in case your tires are bad. I'm giving you like a smallest number for mu-s. Good tires between 1 and 4. You put a 4 here, you can go, imagine if you put a 4 here, how fast you can make that turn. Take the square root of that number. You can make it a 63 meters per second, which means about 140 miles per hour. But again, we're not talking about a small, tight turn here. This is twice the length of a football field. More than twice the length of a football field. Because it's 200 meters. So it's a big turn, so you can go slow.
So what if it's like snowy, what would you?
Well, snow, that number is 0.7. I already covered for that. So that's what I'm saying. When civil engineers go and put these signs up there, they try to think of the worst case scenario. Let's make sure snow tires, snowy outside, bad tires, there's nothing left on them. They use a small number, and they still give themselves some room. It says we came up with 50, they might post the road at 40 miles per hour. It says wet road, 40 miles per hour, dry, 50. Knowing that number changes wet versus dry, That's how they cover for. Now, car racing, for example, when you see it, they go by 100 miles an hour. There's no way that road is going to hold them. If you want to turn like this and you go at 200 miles per hour, I don't care what kind of a tire you got there, you're going to go flying. So guess what they do?
They go up.
Yep, they bank the road. The road is banked. Why is it banked? When you bank the road now, you get the friction force, you get something else pulling back on you to go. What's pulling back on you? Beside the friction force. If this is the road that's banked, let's say theta here. This is your car. You get the friction force this way, and you also got what? mg sine theta pulling down this way. And what do you got pushing in that direction? mv squared over r. And you want these two numbers to equal to each other. Or you want this to be larger than that so you don't go sliding, because that friction force it goes from 0 to that number, can be adjusted any value in between. So you want to make sure the sum of these is equal to that number or less than that number, and that will give them a chance to go 200, 300 miles per hour on that turns without having to worry about it, because now the weight of the car is pulling you down. Actually, if you're going too slow with that car, guess what happens? Slides all the way down, skids all the way down, because the weight of the car. These tires they use on race cars, they're not like, they don't have all the grooves on them. They're not rough like the tires we use in our car. They're one flat one. You see them about this wide, flat. They use them for about 8-9 laps, and new tires goes on $1,000 a piece. They're not cheap, So mg sine theta, that's how they compensate for that. Actually, our book talks about that, banking the road. Planes do the same thing, by the way. When I turn with the plane, if I don't actually do anything to the plane, the tail goes swinging to the outside. So I have to make sure I play with the rudder there to make sure the plane doesn't go flying, because the centripetal force is going to push the plane to go in that direction.
So if you're flying with somebody else, do you have to change the way that you...
Not really, just center of mass. You have to know where the center of mass of the plane, because on takeoff and landing,
Yeah.
if the center of mass, like if you have 4 people in the plane, 2 really heavy and 2 small, you'll see them, you go, you sit here, I sit there, because the center of the plane is crooked a little bit there. Where we use centripetal force, health field. Yeah, when they take sample from your blood sample, you want to separate the plasma. They put them in a centrifuge and they spin at high speed. It can separate that. And again, those things can spin at 800, 900 RPM there, so it's not spinning at lower rate, They have a massive actual acceleration, velocity. So the velocity on these could be like in the 1,000 Gs. I
It
think
needs one of those to mix up the coffee.
to do what?
Mix up the coffee.
Coffee?
Dunkin' Donuts.
Oh, well, not that speed, because I'm thinking about centrifuge. That's in the health field. I'll give you the speed on it, actually. If Dunkin' Donuts used this for coffee, boy. The velocity on these, I can tell you, they had a speed of 90.6, roughly 91 meters per second. That means the acceleration, it's v squared over r. And that centrifuge, if you look at it, it's really, it's about this way, and they have a tube here and a tube here. You got to balance it, by the way. Even if you're only putting one tube, they always put a second one, even if you have to put water in it. Otherwise, the thing is off balance. When it starts spinning, it ruins it. Yep. So if you're only putting one, you put one opposite to it to compensate for the weight. If you have two of them, you put two empty ones there to compensate for the weight. So the radius on the top is really small. It's not that big. Like they close.
Does it matter if you use a big R or a little r?
Well, the big R would make it actually this one smaller. So if you want a high rate,
Yeah.
you want to make sure R is very small. So,
Like upper or lowercase?
oh no, that just me. No reason. I thought it was like, it's better to use small R, like small distance. I know what you're asking. Sometimes I use capital R, sometimes lowercase r. No reason. I couldn't tell you. I'll be writing in something like this in the middle of it. I'll begin with a C and capital F in the middle. I don't know. I have just whatever mood I'm in, you know. So the velocity is 91 here. You're going to square it. And now the radius really, my brother's a doctor. He has a lab and it's about this big. So the radius probably 1 inch pushing it. So that's about 2.2 centimeters. Centimeters. So what is that as a meter? As a meter, that's what? 0.022 meters. Divided by 100. So watch the acceleration on this. How many?
1 inch is actually 2.54 centimeters.
2.54, thank you, not 2.2, 2.54. .025. There we go, meters. So 91 squared divided by .025. There's the acceleration. 331,240 meters per second squared. Oh yeah, if you divide that by 9.8, you know how many G's on it? That's equal 33,800 G's on it. Gravity. Whatever gravity is, multiplied by 33,800 times. So that is like an unbelievable acceleration. That's why everything gets separated there.
I don't think a coffee would make it.
No. Nope. As we said, the movie, was it Apollo 15, when they did the zero gravity with Tom Hanks in the movie? 13, I'm sorry, the Apollo 13, what am I saying, 15? Apollo 13, they used the Comet Vomit, which is a plane that has a certain speed with a certain radius, they can hit zero gravity. Actually, we can do the math there quickly and show you what gravity will be. Let's say the radius, let's pick a radius. Well, we know the speed of the plane, roughly about 500 miles per hour. So the Comet Vomit is going like this, and it's moving. That's actually what they call it, the Comet Vomit, because everyone gets in that. So the velocity of that is, let's say 550 miles per hour. That's normal speed for a 747, 737 when they're cruising. 550 divided by 2.24, roughly 245, 246 meters per second. So the plane start to go in this motion. And let's say this distance roughly 6150, 6,150 meters, the radius. And when it gets to the bottom, it repeats itself. If you want, you can put 652 actually. If you want to put a 52, it gives you zero gravity here. Close to zero gravity. 6152 meters. So when the plane is up there, what's the net force on the plane, or on the people in the plane? On both. The plane doesn't feel anything, so the people will feel that. So you have the weight down, which is mass times gravity. And notice I didn't give you the mass. And we got what? The centripetal force pushing upward, and that's F centripetal equals mv squared over r. Let's plug in the numbers. This is 9.8 g times m. I don't know what the mass is. I left it. That's what the weight is. And what's that number? mv squared over r. Let's take our velocity. The velocity is 246. Let's square it. 246 squared divided by what? 6152. And what do you have? 9.8. See it? So you have m times 9.8, or 9.8 m. Oh, killed that one. Okay. 9.81 m. So, she called me back. I want to talk to you. That's the department chair at Smithfield College. I know what they want. They're looking for somebody to teach a class, and I don't want to do it. If I answer it, I end up doing it. How can I kill it? What do you do to kill it?
Block it.
Well, I don't want to block it. Okay, good, missed call. No. So now notice you got 9.8 m down, you got 9.8 m up. What happens there? 0. So the net force is equal to 0 because the up and down are canceling each other. So you end up with 0. You got down here pushing down is 9.8 m. Pushing upward, we got 9.8 m. The two of them are canceling each other out. So from right there for about 15, 20 seconds, you have 0 gravity. Right there, from here to there, as the plane's going, you get to do a few things. Once it's done, it goes back up there, repeats the process again. 15 more seconds, back up there, 15 more seconds. You keep doing it for about a couple of months, you'll have about 6 minutes of video.
Makes me feel nauseous just by thinking about it.
But yep, you get used to it. You know, you're just floating there.
How long did it take them to film the whole movie?
Oh God, I don't know. But there's only a few scenes with 0 gravity in them, you know. And some they probably took from NASA, directly from NASA, you know, and some actually them. But that's what the centripetal force is. Let's see, my session probably expired again. E-text.